as you see on the screen, that is we are going to talk about Z-bus and symmetrical fault analysis. We are going to start. So let's begin by reviewing what we did in the previous class. So give me a minute. I'll open the previous class notes. Review. So we started talking about the derivation of expressions for bus impedance matrix. We have taken a small system and then step by step how to build it. We did it. So first step, so in this system, first from 0 to 1 I am adding the impedance, then from 1 to 2 I am adding the impedance, then from 1 to 3 I am adding the impedance, and then finally I am adding the impedance between 2 and 3. So 1, 2, 3, 4. We have 4 steps, and in 4 steps we are building the Z-bus. And for each step we have to identify what is the case. So there are 4 cases. So case 1, case 2, case 3, case 4. And we have to identify the case, and then accordingly we have to build the Z-bus. Now if you see, we have also done some derivations in the last class. So this is Cron's reduction, what you are seeing on the screen. So there are 3 equations, 3 unknowns, and whereas the right hand side of one of them is 0, then how to reduce, how to eliminate one of the equations. So I can eliminate x3 and then I can write it in terms of x1 and x2. So how to do that? The right hand side of one of them is 0, then how to reduce, how to eliminate one of the equations. So I can eliminate x3 and then I can write it in terms of x1 and x2. So how to do that? So that's what we have seen. So this is just by multiplication of equations, and this is in the matrix form. So finally, by rearranging all these things, we got this expression to find xn, and then that we have substituted back. Finally, we are getting a reduced matrix. So here b1 to bn minus 1 is a reduced right hand side, and then x1 to xn minus 1 is the reduced unknowns. So if there are 3 unknowns, it will become 2 unknowns, and then the size of this A matrix will decrease. And this is the formula for reduction. So this is also you should kind of remember. Then using that, we just once again repeated cross reduction for this, and we got an example, and we solved one example. So finally, this is the key formula, that is the new A bus will be smaller than the earlier A bus, and the size will be reduced based on this. This is cross reduction formula. Then coming to power system, so I have derived all 4 cases. So this is case 1, this is case 2, where you are adding a new bus to an existing bus, and case 3 is we are adding a existing bus we are connecting to the ground, and finally case 4 is we are adding a new bus between new line between 2 existing buses. So 4 cases, and for each case we have the formula available, and using that formula we are calculating the Z-bus. So that's a quick review. Lecture 20, I talked about 4 formulas for building Z-bus step-by-step method. Lecture 21, I derived the 4 formulas, and we also solved some problems. And I have given some homework. Read the lecture notes, practice, and solve example problems. This is what I've explained in the lecture 21. So far, any doubts up to lecture 21? Any doubts up to lecture 21? Please feel free to ask now before I continue to today's lecture. Mutual impedance is given, then how to find Z-bus. So again, Z-bus with mutual impedance is slightly complicated, but then it's not that complicated. So I would, instead of discussing that in the class, I would refer you to some textbooks to follow that mutual impedance, because it's not that much useful for general everybody's class. So if you're having special interest in it, you can refer to some textbook. That's what I suggest. And we'll begin by finding the Z bus for this particular problem, and then we'll also do fault analysis on the same system. So let me begin by writing down the question on the screen. So the question is something like this. Just a minute. With a 3-bus system. So the system is described like this. There is a generator and the generator is having a transformer here and the transformer is connected to a bus. So this is bus number 1. Then there is another generator and it also has a transformer and the transformer is connected to bus number 2. Now the impedance of the transformer is J0.1 per unit. Impedance of the generator itself is J0.1 and the impedance of this generator is J0.2 and then impedance of this generator is J0.2. Then line 1 and line 2 are connected with a transmission line whose impedance is J0.8. So then we have line 3 here, or let me put the bus 3 here, and bus 3 is connected to bus 1 and the impedance is J0.4. And then bus 3 and 2 are also connected and the impedance of that line is J0.4 per unit again. So all impedances are in per unit this one. So this is a 2 generator 3 bus system. Now the thing that is given here, the generator is star connected and it is grounded. Similarly, this generator is also star connected and it is grounded. So whatever loads that are connected between 1, 2 and 3, other end will also have the same ground that we are showing here. Okay, I think this information is sufficient to go ahead. What is the question? The question is find Z bus. So how do you find Z bus? So Y bus inversion and case B is step by step. So I can build the step by step, or I can first find the Y bus and then invert the Y bus. So we have done several times this thing. The more practice we have, the more better it is, as I have been saying. So this is the first question. So let's do the Y bus inversion method. So what you have to do, first find the Y bus. So how to find the Y bus? So here, you all know that generator can be replaced by Norton's equivalent and then it becomes a current source in parallel with the impedance, and then current source can be ignored because we are only finding the Y bus. So this J.1 and J.1 will become series. So it becomes J.2 and 1 by J.2 will become minus J.5. So here I am doing admittance diagram. Admittance network. So what is the admittance network? So I'll just write bus 1 and then this is the admittance. And this is the ground, 0. And this is minus J5. So how did I get minus J5? This is nothing but 1 by J0.2. So how did I get 1 by J0.2? So this is nothing but bus 1 is connected to the ground using these 2 impedances. So I have to just take the inverse and then I'll get like this. So I hope up to here it is clear. Then I have bus 2. Now the line between 1 and 2 is J0.8. So what is the admittance of that J0.8? So I have to take 1 by J0.8. So let me open my calculator also. .8 is 1.25. So this is minus J 1.25 per unit. This is the admittance of this line. Then what is the admittance connecting 2 to the ground? So 2 is connected to the ground. So here you see the generator is grounded, and J.2 and J.2 are the two impedances. So it will become total impedance is J.4, and 1 by J.4 I have to do. So that will be minus J2.5. So that is the impedance of this line, and this is the impedance. Now I have bus 3 here. So let me show bus 3 here, and then there is a line connecting 1 and 3. What is the admittance of this line? Again J.4, so it is minus J2.5, and then here also there is another line minus J2.5, and there is nothing connecting 3 to the ground to right here. So this itself is the admittance network. And once you have the admittance network, what you have to do next? Y bus. So how do you get the Y bus? Simply by observation, I can get the Y bus. I make 3 rows and 3 columns. We have done this several times in this course. So by now I think everybody should be familiar with this, how to do. So what are the off diagonal elements between 1 and 2? So this is bus 1, this is bus 2, and this is bus 3. So between 1 and 2, minus J1.25 is there. So this will become J1.25. Between 1 and 3, minus J2.5. So the minus sign will go, and then this is the procedure to build the Y bus. The same elements will get copied here because it is symmetrical matrix. Then what about this? This is second row, third column. So this is J. So this also is J2.5 and J2.5. Next I come to the diagonal elements. So I add all the off diagonal elements. So that is 1.25 plus 2.5. That is 3.75. And to that I'll also add the J5, and then finally I put the minus sign. So minus 8.75. Similarly, for bus 2, you see, add all this, so it will be again 3.75 addition of these two, and then 2.5. So 3.75 and 2.5 I have to add. So this will become 1, 2, 6.25. A 6.25 is our impedance. Let me just check that once again. Yeah, it is 6.25. Next, coming to bus 3, I don't have any element connecting to 0, so I can just simply add these two, it will be minus J5. So like this, I have the Y bus. So what is the next step? Next step is very straightforward. Z bus is nothing but Y bus inverse. Now, in order to find the inverse, of course, 3 by 3 inverse with J and everything, we will have to use the MATLAB. So let me go to MATLAB, and then I'll do the inverse of this. So basically, I take J common, so I will not mention J here. I can just put J later also. Minus 8.75, 1.25, and 2.5. This is the first row. Then the second row will be 1.25 minus 6.25 and then 2.5. This is the second row. And finally the third row will be 2.5 and then minus 5. So this is my Y bus. And then Z bus is nothing but INV, inverse of Y bus. So very simple. So now let me run this. So on the right, I'm getting the solution already. So the solution is something like this. So this is the solution. So let me run it once again. So run. So finally I'm getting, this is the Z bus. So here I should ignore the minus sign because j I have taken common, so I'll get minus j. So minus j will be getting multiplied by this. So let me, in fact, I'll do that. I'll put a minus sign at the beginning so that I'll get the magnitude itself. So this one, let me copy it. Bus. So Z bus is nothing but J into this entire matrix. So this is the first method of finding the Z bus. So I hope you are comfortable with this. This is the given power system. I created the admittance network first, and from that admittance network I created the Y bus, and from that Y bus I, using the MATLAB, I inverted, and then finally I got the Z bus here. This is the Z bus. So this is the first method of doing it. So what is the second method of doing it? So in second method, I go for step-by-step building. So let me write that. So basically, I am reviewing the class for you. So this is the second method, building. Z bus step by step. Okay, so in the step one, what I'll do? So I'll consider the generator and I'll consider the transformer and then I'll consider the bus one. And then this generator is grounded. So this is J0.1, J0.2. So here the description I'll write, sorry, this is J0.1 again. So adding J0.2 between 0 and 1. So this is the first step. So this is basically case 1. Case 1 of the Z bus building method. So therefore what is Z bus? Z bus is nothing but Z10. So there's nothing but J0.2. So this is done. So in fact now if I go up, we are getting another bus here. So this part we have taken care. Now I consider this one J0.2, J0.2 connected to bus 2. So what I have to do now? So step 2. So step 2, this is bus 2, J0.2, J0.2. So description is adding total J0.4 between 0 and 2. So basically you see these two are separate networks now. They are two completely separate networks. So again you get case 1 and therefore you get Z bus. So the size will increase because there are two buses. So the earlier Z bus will be like this, 0, 0 will be added and then J0.4 will be the new Z bus. So this is step 2. Now let's continue step 3. Step 3 what I will do is add J0.8, sorry I'll add bus 3 actually, J0.4 between bus 1 and 3. So this is new whereas this is old. So therefore we get the case 3. So let me draw the diagram. So the diagram is like this. So I'll just simply show the impedances. J0.2, then I have bus 1, then J0.4, then I have bus 3. Whereas this part of the network is also there. J0.4 and then bus 2 is already there. So this part is separate, this part is separate, and this I am adding this one. So case 2. So how do you do that? So this is case 2. So between 1 and 3. So So what is the procedure? I think I'll just directly write that here. So Z bus equal to whatever is my old Z bus. So that is J 0.2, J 0.4. This is my old Z bus. So to that I have to copy the first column and copy the first row. So first column is copied J 0.2 and 0. First row is copied J 0.2 and 0. Why I am copying the first row? Because the new bus 3 is connected to the old bus 1. So whatever is the impedance of the 1, we copy that row and column. Then whatever is the Z11, to that Z11 I add the ZB, that is 0.4. So 0.2 plus 0.4, J 0.6 I will get it. So this is my Z bus up to step 3. So I can just put 3 in brackets like this. This is Z bus up to step 3. Now what I will do in step 4? Step 4, I'll just take this network as it is. So I am adding a new line between bus 1 and bus 2. And this is J 0.8. So J 0.8 added between bus 1 and bus 2. So bus 1 is old and bus 2 is old. So between two buses, I am adding the impedance. So I think you are aware what is the procedure. This is case 4. So first what I will do is I will find ZLL. Okay, so what is ZLL? So Z11 plus Z12 plus ZB minus 2 into Z12. So this is my ZLL. So Z11, just go to the previous, it is J0.2 and J0.4. Sorry, this is Z22 plus J0.4 plus ZB. So that is J0.8 minus 2 into Z12, that is nothing but 0 here. So this total thing is becoming how much? 0.4, 0.2 and 0.8. So J 1.4 is my Z11, ZLL. Now what is the delta Z? So delta Z is nothing but, because I am adding between 1 and 2, so I will take the Z2 minus Z1. Or I can take in either way. So if I subtract column 2 from column 1, so what I will get it? Or column 1 from column 2. So I will say column 2 minus column 1. So I will just subtract these two columns. So column 2 is 0, J4 and 0. And column 1 is J 0.2, 0 and J 0.2. So this is my column 1. And when I subtract this, I will get minus J 0.2. Here it will be J 0.4 and here it will be minus J 0.2. So then what is the formula? Z bus new is equal to Z bus old minus 1 by ZLL into delta Z transpose. So this is what we had seen in the previous class as a formula. So first I will calculate this part. So what I should do? So I will just clear this. So what I am typing is delta Z, that is nothing but just now we had written here minus 0.2 I, then 0.4 I, then minus 0.2 I. So this is delta Z, and then ZLL is nothing but 1.4 I, then Z bus, whatever Z bus we have derived up till now is I into this one 0.2, 0, 0.2, 0, 0.4, 0, and then finally 0.2, 0, 0.6, like this. So now I get the Z bus new is nothing but Z bus minus 1 by ZLL multiplied by delta Z into delta Z transpose. So this is the same formula I have applied. So when I execute this, I am getting the Z bus new to be like this. So let me just display the imaginary component of Z bus new. So this is my Z bus. So let me copy this to the main window. Nothing but your Z bus after the fourth step. So what is the next step? So the next step is we will have to add the impedance, the other impedance. That is the final impedance. Minus. So here it is a plus sign. So just a small correction. And once I incorporate that correction, so finally I get this as my Z bus. So this on what you see on the right side is the actual Z bus. So this is the Z bus now. So this is J into all this is nothing but Z bus after fourth step. Now let's continue. So we have the last step, that is step 5. So in step 5, what is left over? So let me get the drawing from the previous case. So I just get this drawing. So this is step 5. So in the step 5, the final addition that I am making to the network is this element. and the impedance is J0.4. So I'll write it here. J0.4 is added between bus 2 and bus 3. So between two existing buses, I am adding the J0.2. So what is delta Z now? This is nothing but second column, or I can take any order. Third column minus second column. So this is what I have to do. So I already have the Z bus here. So the column 3 minus column 2 I have to take. So since I have the code, so I'll do it in that. And what is ZLL? So ZLL is nothing but Z22 plus Z33 plus ZB minus 2 into Z23. So let's do that calculation here. So Z22, even I have that here. This is Z22, this is Z23, and this is Z32. So I have all the values. So I have to, through that I have to do that. So I think again to do this new Z bus, again I'll continue the program. So let's go back to the Z bus. So I'll just simply update this Z bus. So this is, I'll write here step 4. Adding J0.8 between 1 and 2. That was step 4. So step 4 calculation is over. Then step 5. Adding J0.4 between buses 2 and 3. So this is just a comment so that for you it is easy to read. So what you have to do first, delta Z. So delta Z is nothing but Z bus all rows second column or all rows third column minus all rows second column. So basically I am taking the subtraction third column, from third column I am removing the second column. That is the code that you are seeing on the screen. Then from this I will also get ZLL also I will calculate. So ZLL is nothing but Z bus 2 comma 2 plus Z bus 3 comma 3 plus J 0.4 minus 2 into Z bus 2 comma 3. So this is what is the formula. So again, in the previous lecture we have derived this. I am just whatever we derived in the previous lecture, I am just implementing it here. So from this I can get what is my new Z bus. Just the same formula I will copy. So from this I will get the new Z bus. So let's run this. So that's it. The program is completed. So on the right you can see the final answer here. So let me display the imaginary part of it. Imaginary part of Z bus. So finally on the right side you are seeing the final solution. This is what is the final Z bus after bus 5. So let me copy this solution. So copy this solution to our screen. So from MATLAB code, so this is my Z bus. So J J into this is my Z bus. So finally my Z bus is something like this: 0.16 J, J 0.16, J 0.08, J 0.12, J 0.08, J 0.24, J 0.16, J 0.12, J 0.16 and J 0.34. So this is my final Z bus. Of the given network. Now, if you compare, we did two methods. So, first method is finding out the bus admittance matrix and inverting it, and the second method is step-by-step building. And both methods you are getting the exactly same answer. So, this answer is exactly same as what we got in the previous case. So, that's a very good verification of two methods. So, once again, I'll pause here for a while. If you have any doubts in what you have done, let me know. I have not done anything new. Already I told in lecture 20, same thing I repeated lecture 21, same thing I repeated lecture 22. Just it's a review of what we had done in the previous lecture. The cases I have described, the same cases I have implemented and solved a 3-bus system. So finally you are getting the Z bus like this, which is matching with the existing one. So at this stage, I feel that the topic of Z-bus building is completed. I would like to go to further new topic, that is symmetrical fault analysis. But then, if you have any doubts, so let's pause for a while, and then if you have any doubts, please feel free to ask them right now regarding how to build the Z-bus and all. The lecture notes, you can refer to it. So So in symmetrical fault analysis, what we try to do is study study the effects of three-phase faults. So consider there is a generator, and the generator is actually a three-phase generator. It is connected to a bus bar. This is a single line diagram. So there will be a phase, B phase, and three phase. So there will be three bus bars for three phases and all. This is just a single line diagram. And the fault occurs at this bus bar. This is a three-phase fault. That means phase A, phase B, phase C, all of them are short circuited, and together it is short circuited to the ground. Three-phase fault is this one. So this is also called LLLG fault. All the three lines are short circuited, and then it is short circuited to the ground also. So in that case, whatever the voltage that generator was generating, by definition now the voltage will be equal to zero, because when there is a fault, the voltage becomes equal to zero. Of course, here the fault impedance is being neglected. Now, under such conditions, let's say there is a circuit breaker. So this is a circuit breaker. Circuit breaker is a protective device which can break the circuit whenever there is a fault occurred. So here you measure what is the fault current, and then if the fault current is more than a certain value of current. So for example, for a three-phase fault, the fault current is 2000 amperes. So if the current that you calculate in your analysis 2000 amperes, you will make the relay setting to be somewhere around 1800 amperes or 1500 amperes. So therefore, whenever there is a fault occurs, the fault will be more than your setting, and then the fault is detected and the circuit breaker opens, and then the circuit gets disconnected. So that is the scenario. So here the reactance of the generator. So generator reactance varies during the fault. So for why it varies and what is the background theory and all, for that you need to learn, the machine design and all the topic. So you have to go into stability studies and all. But for our discussion, I define something called sub-transient reactance. Then there is something called transient reactance, and finally something called synchronous reactance. So these are the three different types of reactances that a generator has. Now the subtransient reactance is denoted by XD double dash, and the transient reaction is denoted by XD single dash, and finally the synchronous reactance is defined as XS. So synchronous reactance is this is under normal operation. So when there is no fault and your transformer is operating under normal conditions, at the time the reactance of the transformer is represented as XS. Now X double dash is the reactance under fault condition. So I'll write few cycles after fault. That means immediately after the fault, 3 or 4 cycles, that whatever at that time, during that time, whatever is the reactance offered by the generator is XD double dash. And XD single dash is nothing but is a transient. So subtransient means below transients and transient means at the time of transient. So this is during actual fault. So at this time, this is like a few milliseconds after the fault has occurred. So this is maybe up to 100 milliseconds. So less than 100 milliseconds, and this is greater than 100 milliseconds. I am just assuming as a 5 cycles. So first 5 cycles I consider transient reactance. In fact, these are all only artificial divisions. Physically, the transient, there's nothing like step change between XD double dash and XD dash. The impedance keeps changing gradually, but then we consider like that. Now, so for us, what is important here is which is used for which study. So, XD double dash is used for stability and transients, and XD dash is used for stability only, and XS is used for load flow studies. So this is also fault calculations. So if you want to do fault analysis and all, XD single dash is used, and this is load flow studies. So we have been using XS for our system. Okay, so now with this brief introduction, what we are interested is, given the generator, suddenly there is a fault. What is a fault current? So that is what we are interested in. So I just very basic toy problem I'll give you. So to start our analysis. So this is find the fault current. If uh, fault occurs at bus bar of three-phase generator with XT dash equal to J0.1. Also, so here generator is running on no load. with rated voltage. So rated voltage is V is 1 per unit. And also fault impedance is J 0.05 per unit. So this is the data is given to you. So it's not very difficult. What you have to do is, first I'll draw the circuit for this this one. There is a generator. Generator has XD single dash is J 0.1, and then we are generating voltage of V equal to 1 per unit. So this 1 per unit, and then there is a fault which is occurring here. So the fault symbol is like this, and then similarly this is a fault, and the fault impedance is J 0.05. So now the objective is to find the fault current. So this current, let's denote this current as IF. So what is IF? So the way to solve this is, actually the theory behind this is coming from the Thevenin's network. So what you do is that you short circuit this generator. That means you replace this generator by a simple short circuit. So then here I have XD dash, that is J 0.1. Then this pre-fault voltage, whatever it is, that you put it as a voltage source in this direction. So 1 per unit, and then finally this impedance is there, J 0.05, and then finally it is there. So now what is the fault current? I can easily calculate. So you short circuit all the generators, then you represent it in the form of a network, and then here you have one single source. This is a pre-fault voltage. So V Thevenin is nothing but this is V Thevenin. There is nothing but pre-fault. That means before the fault occurred, what is the voltage? So pre-fault voltage is 1. So simply fault current is nothing but 1 by total impedance. That is J 0.1 plus J 0.05. So that is 1 by J 0.15. So that is, so let me just quickly calculate that. So we get 6.66 per unit. So this is minus J. So that means almost 6.66 times the rated current we are getting. So high current, 6.66 per unit. What is the voltage now? Post-fault voltage. So the bus bar here, because there is a fault, the voltage has reduced now. It will not become completely zero. So, but what is the post-fault voltage? So nothing but IF into ZF. So V1 equal to. So minus J 6.66 into J 0.05. So this is nothing but .66 into 0.05. So I am getting J into J is minus 1 and the minus will get cancelled, 0.333 per unit. So the earlier before the fault, the impedance was, the voltage was 1 per unit, and suddenly the voltage is falling to 0. So suddenly there is a low voltage. Of course, it is expected because there is a fault. So the two important things, conclusion that we find is the fault current is 6.66 per unit, and the fault voltage is, after the fault, the voltage is 0.33 per unit. Very short problem, just a simple generator and with a synchronous reactance, the transient reactance is given to you, you are able to find the fault current. So let's, any doubts up to here? Okay, so if you don't have doubts, let's go to one bigger problem, a circuit diagram which we saw in the first part of this lecture. So this is another generator. So This is nothing but your XD dash. The subtransient reactance of the generator is given. And then there is a transformer once again, and this transformer also having the impedance of J.2. Then there is a bus 2, and between bus 1 and 2 I have an impedance of J0.8, and then between bus 1 and 3 I have an impedance of J0.4. This is bus 3, and then between bus 3 and 2 also I have impedance of J0.4. So this is the network diagram given to you. Now what are the assumptions? So there are some assumptions we are going to see here. So the first assumption is V1 equal to V2 equal to V3 equal to 1.0 per unit. So the second assumption is no load on the network. So you notice I have got a small power system. I have shown two generators, but there are no loads. There is no load at bus 2, there is no load at bus 3, there is no load at bus 1. So completely there are no loads at all. So if there are no loads, what will happen? There won't be any current flowing between line 2 to 3. The current between 1 to 3 will be 0. All the currents will be 0. So that means the currents will be 0. So because the currents are 0, there are no voltage drops, and therefore all voltages are 1. This is just an assumption. And another assumption is shunt impedances are neglected. That means there is a charging impedance for this line. Okay, so the pi model of the transmission line, all such kinds of things we are neglecting because we are interested in calculating the faults. So another simplifying assumption is resistance is neglected. So basically what happens if there is some resistance in this circuit, so in order to maintain the voltage levels, some current will flow, there will be some power loss and all these things that we are neglecting right now. So these are the assumptions. Now what is the question? So the question is like this. Fault impedance ZF is nothing but J0.16 per unit. So this is the fault impedance, and then fault occurs, it's a three-phase fault occurs. At so bus 1, case B is bus 2, case C is bus 3. So these three are three different scenarios. So under each case, what is the fault current? So if there is a fault at bus 1, what is the fault current? Separately, if there is a fault at bus 2, what is the fault current? And similarly, fault at bus 3, what is the fault current? So this is the question. Similarly, what are the post-fault voltages? So before the fault, pre-fault, the voltages are 1, 1, 1. So all voltages are equal to rated voltage. But if there is a fault occurs and after the fault, what happens to the voltages? The voltages of course will reduce. So how to calculate what are the voltages after the fault? So this is the question that we have to solve. Now let's take the first case. Let's take there is a fault at bus 1. So then what happens to our circuit? So let me redraw the circuit. The circuit, I have a generator here. This part is grounded, J0.1. Then I have a transformer J0.1. Then this is the bus 1. Here there is a fault, and then the fault impedance ZF is 0.16 J. Now between 1 to 2 there is a line J 0.8. Between 1 to 3 there is a line J 0.4. Between 3 to 2 also there is J 0.4. And then here also there is a generator J 0.2 and there is a transformer of J 0.2. So this is bus 2. This is bus 1. No load at any other place, just only this fault is there. So what you have to do is, in this case, you have to find the Thevenin's impedance. So what is the procedure? To find the fault current, remember last time what we did, all the generators you simply short circuit with their the transient reactance. So this branch, so this is step 1. So what we are doing in step 1, we are highlighting where the fault has occurred. The fault has occurred on bus 1. So now what is the step 2? So this is Thevenin's equivalent. So what you have to do is just short circuit the generator here, and then J 0.2 we have here. This is bus 1. This also you short circuit. Then I have J 0.4 here. So you see these two are in series, J 0.2, J 0.2. If there are any other generator, that also you can see. By the way, what is the path of the fault current? So the fault current is like this. This is IF. So some current will come from here, some current will come from this. There are two generators. So this is IF1, this is IF2. Then the IF2 will split into two parts, and then the current will flow like this, and then some current will flow like this, and finally all the currents will meet here and then go into the fault current. So this is the circuit that we are getting. So therefore what I do is simply do the circuit. It is basically like a circuit analysis now. So this is 2, then this is J 0.8, then this is bus 3, so J 0.4, and then here it is, so this is bus 3, and the fault is here, J 0.16, this is the fault. So here I'll introduce a VTH, plus sign here, minus sign here. This VTH is nothing but 1.0 per unit, that is post fault this thing. Now for this circuit I want to find the current. Now you notice these two are in series. So I get the circuit to be, these two are in series. So J.4 plus J.4. So this is J.8. That part is in parallel with J.8. So J.8 parallel with J.8. So then the equivalent will be J.4. The J.4 is again in series with J.4. So what I'll get? So J.4 plus J.4. So I'll get J.8. So this will become J.8. I'm sorry, I might be confusing you. So let me just, to avoid the confusion, let me just draw the subsequent networks. That way it will be much clearer. See, this network is equivalent to J.2, J.4, J.8, and then J.8. This is 2, this is 1. And here I have the VTH and the fault. Now these two are in parallel. So what I'll get now? So I'll get J.2, and then this branch will become J.4, and then this branch will become J.4, and this is grounded, this is grounded, this is bus 1, this is bus 2, and the fault is here. So now these two are in series and that overall thing is in parallel with. So finally I'll get so this is J.8, this is bus 1 and this is J.2 and then there is a Thevenin's impedance and then there is a fault impedance J0.16. Then finally what is this one? So I'll get 0.2 parallel with 0.8. So 0.2 into 0.8 by 0.2 plus 0.8. So I think it is 0.16. 0.16, this is the ground. Then I have the bus 1. Then I have the Thevenin's voltage. This is nothing but 1.0 per unit. Then finally I have the fault impedance. So what is fault current? So simple Ohm's law I can apply here. So fault current is nothing but 1 divided by J.16 plus J.16. So let me just calculate that. 1 divided by 0.32. So this will be minus J 3.125 per unit. So this is my fault current. When the fault is at bus 1. Now I can also ask the question, how much of current is coming from each generator? So if I just go up one step, so here the fault current is this much. So there are two branches. So this branch completely coming from first generator, this branch is completely coming from second generator. So I can calculate what is the fault current coming from the first branch simply by using the current division rule. So 0.2 and 0.8 you can see. So by current division, rule, fault current from generator 1 is nothing but minus J 3.125 multiplied by 0.8 divided by 0.2 plus 0.8. So why am I doing like this? So this is just a current division principle. So J I can ignore because it will just anyway cancel. 0.8 is the impedance of the opposite branch and then 0.2 is the impedance of the branch in which you want to calculate the impedance. So this is 0.08. So 0.8 plus 0.2 is 0.1. So just 0.8 of this one. So 3.125 into 0.8. So that will be 2.5 per unit. So this is the fault current coming from the generator 1. So fault current from generator 2 will be nothing but minus J 3.125 into 0.2 by 0.2 plus 0.8. So that will be minus J 0.625 per unit. So this way, this is I fault 1 and I fault from generator 2. So I am able to find the total fault current and fault currents for these generators. I can also find the voltages. So what is bus 1 voltage? So post fault V1 is nothing but IF into VF. Sorry, IF into ZF. So fault current was minus J 3.125 and fault impedance is J 0.16. So if I multiply these two, I'll get the impedance. 3.125 into 0.16. So that will be 0.5 per unit. That is post fault V1. So immediately after the fault, the voltage is falling to 0.5 per unit. Now what about the voltage of when there is a fault at bus 2, what happens? So far any doubts regarding the procedure what we have done? It's basic circuit calculation. Whenever there is a symmetrical fault at any bus, you short circuit all the other generators and then find out you solve the circuit and find out the Thevenin's impedance up to that point by series parallel combination of everything, and then finally you will get the fault impedance. It becomes a simple circuit. So for example, here what I have done, first step I have just merged these two. Second step, this two series terms I have added. Another step, then this J.8 will become J.4, so 0.4. And then these two are in series. And then finally, by solving it as a circuit, I am getting this. So any doubts up to here? So before we continue, let me just write one thing here. So this one is the Thevenin's impedance. Thevenin's impedance of bus 1 or at bus 1. So 0.16 was the Thevenin's impedance at bus 1. We did this after some calculation. So we had to do so many circuit calculations. Finally, we found that. Okay, now what happens if there is a fault at bus 2? So now let me go to the fault at bus 2. So what we have to do now? We have to find Thevenin's impedance at bus 2. That's all. So first let's begin to find that Thevenin's impedance at bus 2. So I hope by now you already remember the circuit. So here this is J0.2 and then this is J0.8 and then here I get bus 2, this is bus 1 and bus 3 J0.4, here we have bus 3 and then J0.4 is here and then here J0.4 is all again here. So this is there. So I want Z22. So taking this as reference, what is the impedance seen at bus 2 between 2 and the ground? So these two are in series. So I get like this. This is 1, 2, 0.8 J, another J.8, then here J.2, here J.4. So this is one step. So what happens next? So I get J.2 and then here J0.4 and then this one also is J0.4. This is bus 2, this is bus 1. Now at this point I want impedance. So these two will become series. So finally I'll get J0.6 in parallel with J0.4. I'm sorry. This is the ground. This is also the ground. So this is bus 2. This one. So what is the Z22? Z22 is J, so Z1, Z2 by Z 0.6 into 0.4 divided by 0.6 plus 0.4. So 6 into 4 is 24, 0.24. J into J, it will become minus, and then at the denominator I'll get 6 plus 4 is 1. So J1. So finally J will go up and then it will become J0.24 per unit. So this is Z22. So I have a simple network now, J0.24, then this is bus 2, then I have Thevenin's VTH, and then I have the fault impedance. J0.16 was given. So finally, what is the fault current? Fault current for bus 2 fault is nothing but, so 1.0 divided by J0.24 plus J0.16. So let's do that calculation. So 1 divided by 0.24 plus 0.16. So this is 2.5 per unit. So this is the total fault current when there is a fault at bus 2. So I hope again you are able to follow this. I have not done anything basic circuit analysis. Just simply find the Thevenin's impedance and then find the fault. So just remember this also, Z22 is J0.24. Now again I can find the fault current coming from first generator, fault current coming from second generator and all. IF1, you can see just here 0.6 and 0.4 are there. So IF1 is 2.5 into J0.4 by J0.4 plus 0.6. So that will be J1. Oh, by the way, sorry, this will be minus. So this is minus. So fault current from first generator is 1 per unit, and fault current from second generator will be minus 1.5 per unit. This I don't have to calculate because the total has to be minus 2.5. So we can also find the voltages also. So what is V2 post fault? So voltage of bus 2 after the fault is nothing but IF ZF. So J0.16 into minus J 2.5. So that will be 2.5 into 0.16. So 0.4 per unit. So when there was a fault at bus 1, notice that bus 1 voltage went to 0.5 per unit. But when there is a fault at bus 2, the voltage went to 0.4 per unit. This is not allowable. So always the rated value, the voltage should be 0.95 to 1.05. This is the permissible voltage limits. So 5% less or 5% more is the permissible voltage limits. So when the actual voltage is 0.4, that means there is a fault. So that is how this analysis will be helpful for us. Now let's do the last case. Last case is slightly tricky. So fault at bus 3. So you once again draw the circuit. The circuit is like this. I just put the ground here, J0.2. Then I have bus 1. Then I have J0.8. Then I have bus 2 here, J0.4. Then I have J0.4 and then J0.4, and then here is the bus 3. Now how to find? So unfortunately there is a delta connection forming here. So to find the Thevenin's impedance at bus 3, you have to find the equivalent star for this delta. So delta to star conversion. So how to do delta to star conversion? So This is J.2. This is J.4. Now I get a star point here like this. This is bus 3, this is bus 2, this is bus 1. So what is the value of this? So you might remember from your circuits this one. So 0.4 into 0.4 divided by 0.4 and so on. So I'm not going to show you the formula, just I'm writing the conversion. So this is what you will get it. So after the conversion, so again you can just find this. This is J.3 and this point is star point, and then this is J.6. This is ground, and then this is J.1. Finally, this is bus 3. So 0.6 and 0.3 are in parallel. Then what you get? So 0.6, 0.3 in parallel. 0.6 into 0.3 divided by 0.9. So 0.2 it will be. This will be 0.4 and 0.4 and 0.6 are in parallel. So this will be 0.24 and then finally this will be J0.1 and finally this is bus 3. So here I'll get finally the Z33. So 0.1 plus 0.24, Z33 is J0.34 per unit. So once I have this Z33, I can find the fault current, that is nothing but 1 divided by 0.34 plus 0.16. That is 1 by 0.50. So that is 2 per unit is the fault current. And then you can always find the fault current with first generator, so minus J2 and so on. Which I am not doing because I am running out of time. So one thing I would like you to notice now is what are the values of Z11, Z22 and Z33. These are nothing but Thevenin's impedance at bus 1, Thevenin's impedance at bus 2 and Thevenin's impedance at bus 3. If I know these values, then it is easy to calculate the fault current, isn't it? So if you know the Thevenin's impedance already, you can easily calculate the fault current when the fault impedance are given. So let me make a note. So what is Z33? It is J0.34. What is Z22? So if I refer to my notes before, so I made a note here, J0.24 is Z22. J0.24 and J0.16 was the Thevenin's impedance at bus 1 that we solved in the in today's class. Now we also calculated the Z bus. So let's look at the Z bus. So I will paste the Z bus from a different problem. Yeah. So we calculated the Z bus. I'm just copying it. So this is the Z bus. So what is the interesting thing you find? So the Z bus diagonal elements, this is nothing but Z11, this is nothing but, so this is nothing but this and this is nothing but this. So therefore if you if you created the Z bus, then you don't have to calculate the Thevenin's impedance for every bus. It is very easy. So therefore, if you have the Z bus, so for example, the network is given. So then you find the Z bus of the network. Then the fault can be anywhere. Fault can be at bus 1, fault can be at bus 2, bus 3, bus 4, anywhere there is a fault. You can immediately calculate the what is the fault current by using this Z bus. So that is why Z bus is very useful and important for fault calculations. So any doubts you have so far? I hope you understood what we tried to do today. So refer back to the notes and then see. So if you have any doubts right now, you can ask. I'll just pause for a minute.